lot of complicated explanation, but the easiest way to see this equation in action is just to do. So we are going to use Bohr's equation to calculate the amount of energy that is released by hydrogen. Again, his equation was specifically optimized for hydrogen. And the electron we are going to be observing is going to be falling from the 5th shell down to the 2nd shell. So we are starting on our ladder at position n equal to 5, and we are going to be falling down to n equal to 2. So our electron's here. We're going to be falling all the way down here. A certain amount of light with a particular energy signature is going to be given off. The energy is going to be what we calculate. All right, so take some time, see if you can't plug in the numbers yourself, figure out where the n's are going to be going, calculate your energy, and then we will compare our answers. All right, welcome back. Let us calculate the change in energy that is going to be required in this electron. Our delta E is what we are looking for. This will be equal to the negative 2.178 times 10 to the negative 18 joules. And we're going to multiply that by the terms that actually contain the n's. So we have two different n's. We are starting at n equal to 5. We are falling down to n equal to 2. All right, so the ending place, the final resting place of our electron is n equal to 2, right? Final, we can think of as final resting place. The electron then, since it fell to n equal to 2, we are going to take that 2 and we are going to square it in the first term here. We're going to subtract out 1 divided by 5 squared, since the 5 represents the initial position of our electron, where it started. And now we have just one equation and one unknown to solve for, which is our delta E. So in crunching our numbers, what we find is an energy difference of negative 4.574 times 10 to the negative 19 joules, where again, the negative sign here is directional, meaning that this is the amount of energy that is emitted. It is leaving the atom. Now the energy signature is very, very tiny, right, on the magnitude of 10 to the negative 19. But as we have already talked about when it came to looking at the general properties of light, as well as some wave-particle duality kind of calculations, energy values on the scale of 10 to the negative 18, 19, 20 are all to be expected when we are observing very, very small quantum phenomenon. This is a single electron dropping and then releasing one photon of light that has this particular energy to it. All right, so we have now the magnitude of energy, but as we kind of already previously hinted at, if we are assuming that this energy is being emitted in the form of light, and if we know the energy of the light, we know the wavelength of light, we can also calculate what is the color that is emitted. If we were to observe an electron falling from n equal to 5 down to n equal to 2, what would it look like to us in terms of signature wavelength? Well, we can use our equation that we've already discussed, again, and kind of reiterated earlier, and again, rewritten here. Energy is equal to Planck's constant times the speed of light, all divided by wavelength, to find wavelength. All right, we're also going to find the wavelength in nanometers, which is what is written in the wording of this problem, since the nanometer scale is where the visible spectrum lies. All right, so same problem. I just have specifically rewritten that we're going from the 5th shell to the 2nd shell, just to make it really clear that this is the same electron we are observing the fall of. All right, so since we have energy and we know these two constants, we can solve for wavelength. So I'd like you to try that now. All right, so let's calculate this wavelength. So in rearranging this equation algebraically, in order to solve for wavelength, what we have to do is multiply wavelength up and divide energy down. So the wavelength is going to be equal to Planck's constant times speed of light, all divided by E. Now the E that we have found already, our delta E, on just the previous slide, was negative 4.574 times 10 to the negative 19 joules. So if we take this E and plug it into our equation, we may have observed a little bit of an issue, where this E is negative, and wavelengths can't be negative. So what do we do about this? Well, it's sort of unwritten in this equation, but here's how we get around this. The E, or rather the delta E that we just calculated, was negative because the sign is directional. Is the energy going into the atom, or is it leaving the atom? The negative sign has nothing to do with the actual magnitude of the energy. The magnitude of the energy is still 4.574 times 10 to the negative 19. And we only need to know the magnitude of energy, in order to plug this into the equation and find our wavelength. What this means at the end of the day is that this delta E with its negative sign being directional is all well and good, but the E that we plug into our equation up above to solve for wavelength is an absolute value. It's an absolute magnitude. So we can take the absolute value of our energy and insert that in for the energy in our equation here to solve for wavelength. In other words, we can drop the negative sign. I'm using fancy math terms to describe what is, at the end of the day, just us dropping the sign, because when it comes to solving this new problem, the sign doesn't matter. We can drop it. All right, so our wavelength is going to be equal to Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And we're going to multiply this by the speed of light, 2.998 times 10 to the 8 meters per second. We're going to divide all of this by E, 4.574 times 10 to the negative 19 joules. All right, so here we can see that joules are going to cancel, seconds are going to cancel. This is going to give us a value of the wavelength in meters. And the value of our wavelength is going to be 4.346 times 10 to the negative 7 meter. Now, we were asked to find this wavelength in nanometers. The reason being, again, is this is going to give us a more direct observation of where it falls in the visible spectrum. So I'm going to take this number, and I'm going to move my calculations up here because I'm running out of space. I write too big sometimes. 4.346 times 10 to the negative 7 meters. And we are going to convert this into nanometers using the conversion of 10 to the 9. Again, 9 starts with an N, nanometer starts with an N, and this is how we can remember exactly which conversion it is that we need. So meters cancel out, we're tacking on a 10 to the 9 here, giving us a final wavelength that is 434.6 nanometers.